Right now, plugged into your wall, there's a device doing something that should, by the laws of physics, be impossible. It's taking electricity that could kill you, shrinking it down, changing its entire nature, and doing it 100,000 times per second in a box the size of your thumb. And when it gets hot, that heat isn't random. That's tiny components, smaller than a grain of rice, fighting to control dangerous electricity before it reaches your phone. Most people think a charger just charges. By the end of this video, you'll never look at that little white brick the same way again. Let's start with what's actually coming out of your wall. Your wall outlet delivers 220 volts of alternating current. In India, that means the electricity is literally reversing direction 50 times every single second. It surges and collapses, like a wave. Your phone needs 5 volts. Direct current. Perfectly smooth. Perfectly stable. That's not a small difference. That's a 44 times reduction in voltage, a complete change in the type of electricity, and it has to happen fast enough that your phone never even notices. A device that does all of that should require a room full of equipment. Transformers the size of refrigerators, industrial converters. Instead, it fits in your pocket. Here's how. For most of the 20th century, chargers were massive. Early power supplies used what engineers called linear regulators, big, heavy iron core transformers that worked by brute force. They converted electricity the slow, wasteful way. The leftover energy, it just became heat. These things were heavy, hot, and huge.
Then in the 1970s, engineers started experimenting with something radical. What if instead of slowly transforming the electricity, you switched it on and off thousands of times per second? It sounds insane. But switching fast enough, it turns out, lets you control power with incredible precision, using components 100 times smaller than before. They called it the Switched Mode Power Supply, SMPS. It was one of the quietest revolutions in electronics history. No fanfare, no famous inventor, just a fundamental idea that slowly shrank from cabinet-sized industrial equipment to the brick on your desk, to the chip inside your phone case today. Here's the whole charger broken into 4 things. 1. Filter. Clean up the dirty electricity coming from the wall. 2. Switch. Chop it on and off insanely fast. 3. Transform. Use that switching to step the voltage way down. 4. You regulate. Keep the output perfectly stable no matter what. That's it. 4 jobs. Every component inside that charger is doing one of those 4 things. Now let's go through what actually happens. Step by step. Step 1. The electricity enters, and it's a mess. Wall current in India is 220 volts AC. AC means it's alternating, flowing forward then backward 50 times per second. Picture a river that reverses direction twice a second. That's what's entering your charger. The first thing the charger does is rectify it, using components called diodes that act like one-way valves. They only let current through in one direction. The result? The wave stops reversing. It becomes bumpy DC, flowing in one direction but still rising and falling in voltage. Then capacitors smooth it out. Think of a capacitor like a small water tank. It fills up when voltage is high, releases current when voltage dips. The result is relatively stable high voltage DC, around 300 volts, sitting inside your charger. But here's where it gets interesting. Step 2, the switching begins. That 300 volts DC hits a component called a MOSFET, a tiny transistor that acts as an incredibly fast switch. And when I say fast, I mean fast. This switch opens and closes between 50,000 and 200,000 times per second. You can't see it. You can't hear it. But right now, inside your charger, something is switching on and off faster than the fastest hummingbird wing you've ever seen. Why switch it? Because a transformer, the component that steps voltage down, only works on changing current, not steady current. By switching the DC on and off at high frequency, you're creating an artificial alternating current. One you control completely. And here's the genius. The faster you switch, the smaller the transformer needs to be. That's why modern chargers are tiny. They're switching so fast the transformer only needs to be a fraction of the size of old ones. Step 3, the transformer. Now the high-frequency switching current hits a small transformer. 2 coils of wire wrapped around a tiny ferrite core. The input coil creates a magnetic field. The output coil catches that field and converts it back to electricity, but at a lower voltage. The ratio of wire turns determines the ratio of voltage. More turns on the input side, fewer on the output, and voltage drops. from 300 volts down to around 5 to 20 volts. But there's something else the transformer does that most people never think about. It creates electrical isolation. The input side and the output side never actually touch. The only connection is a magnetic field. That means the dangerous 300 volts on the wall side can never directly reach your phone. The transformer is a silent wall between you and electrocution. Step 4. Regulation. The smart part, the voltage coming out of the transformer isn't perfectly stable yet. It varies depending on how much your phone is drawing. So a feedback circuit monitors the output voltage constantly. If it dips too low, the MOSFET switches faster. If it climbs too high, it switches slower. The whole system is continuously self-correcting, thousands of times per second, keeping output voltage rock solid. Modern fast chargers like 65 watts or 120 watts, they have a two-way conversation with your phone, a protocol called USB power delivery, where the charger asks, "How much voltage do you need?" and the phone replies. Then the charger adjusts in real time. Here's what's actually happening when your charger warms up. Every time that MOSFET switches, 100,000 times a second, it loses a tiny bit of energy as heat. The transformer loses some. The capacitors lose some. There are also tiny resistances throughout the circuit, and energy bleeds out through every one of them. A well-designed charger converts around 85 to 92% of input power into useful output. The rest becomes heat. That's actually incredible efficiency. But even 8% of, say, 65 watts is over 5 watts of pure heat, continuously, in a space smaller than a matchbox. When your charger gets uncomfortably hot, one of three things is happening. It's working hard, it's poorly designed with cheap components, or ventilation is blocked. And here's the part most people don't know. Cheap chargers cut corners on the capacitors and the feedback circuit. That means voltage spikes can get through. Improperly regulated voltage doesn't just wear your battery out faster, it can, in rare cases, damage the charging IC inside your phone entirely. The price difference between a 150 rupee local charger and a 1,500 rupee original one? It's not the cable, it's the quality of those 4 steps happening inside. Most people don't know this, number 1. Your charger uses power even when your phone isn't connected. That MOSFET is still switching. Capacitors still holding charge. It's called standby power drain, and across millions of households, idle chargers waste a measurable amount of electricity every year. Most people don't know this, number 2. The ferrite core in your charger transformer, that tiny gray or black piece, is essentially a form of compressed rust, iron oxide particles sintered under high pressure. It's been engineered to handle high-frequency magnetic fields without heating up and destroying itself. Most people don't know this, number 3. The clicking sound some cheap chargers make? That's the switching frequency dropping into the audible range, below 20,000 Hz. A well-designed charger operates above human hearing. When you can hear your charger, it's a sign the regulation is unstable. So here's the thing. That small white brick isn't passive, it isn't simple. It's one of the most quietly sophisticated devices in your home, doing complex power conversion at superhuman speed, thousands of times per second, with built-in protection, feedback loops, and isolation, all while sitting unnoticed behind your bed. The heat you feel? That's the cost of physics. The price of moving energy from one form to another is that some always escapes. Every charger that's ever worked perfectly was a machine doing something extraordinary. Invisibly, silently, and completely taken for granted. Now, here's something even more interesting. Your phone battery doesn't actually store electricity, it stores chemistry. And every time you charge it, you're triggering a controlled chemical reaction inside a tiny sealed pouch. A reaction that, if it goes wrong, releases energy equivalent to a small explosive. How does your phone know when to stop that reaction before it destroys itself? That's the next video.